Hi everybody, in this recording we will be going over section 4.5, integration by substitution. In this section we are dealing with composite functions, particularly the integration counterpart of the chain rule. So we let g be a function whose range is an interval I, and we let f be a function that is continuous on I. If g is differentiable on its domain, and capital F is an antiderivative of f in the interval I, then the indefinite integral of f composed of g of x times g prime of x with respect to x is equal to our antiderivative f composed of g of x plus our constant c. So we let u be equal to g of x, so u substitution, which gives that du, or the derivative of u with respect to x, is equal to g prime of x dx. And the integral of f of u with respect to u is equal to the antiderivative f evaluated at u plus our constant of integration. So the chain rule states that the derivative with respect to x of our antiderivative composed of g of x, so our antiderivative f composed of g of x, is equal to capital F prime composed of g of x times g prime of x. So we take the derivative of the outside, so f prime, leave the inside the same, g of x, and multiply by the derivative of the inside, g prime of x, right here. So now we are going over an example of integration by substitution. So we are told to calculate the indefinite integral of x squared plus 1 raised to the power of 2 times 2x with respect to x. So we let g of x be equal to x squared plus 1, so the portion that we will be substituting right here. This will be our g of x. Then g prime of x, so the derivative of these two terms, will be 2x, just using the power rule. So we have 2 times x, and then derivative of a constant is 0. So that means that the indefinite integral will be plugging back in our g of x raised to the power of 2 times g prime of x with respect to x. So the indefinite integral, recall, was our antiderivative composed of g of x plus our constant of integration. So then the integral of g of x to the 2 will be g of x to the 2 plus 1 divided by 2 plus 1. So that's why we have g of x to the 3 divided by 3 plus our constant of integration. So then plugging back in our initial expression, we have x squared plus 1 raised to the power of 3 divided by 3 plus our constant of integration because we have an indefinite integral. And we just matched the pattern from the chain rule. However, this can get messy. So we're told to calculate the indefinite integral of 5 times cosine of 5x with respect to x. So we let g of x be equal to 5x, so the derivative of that is equal to 5. So then that means that our indefinite integral will now be cosine, now we will be taking the indefinite integral of cosine of g of x times g prime of x with respect to x. So that will be our antiderivative f composed of g of x plus our constant of integration c. So the antiderivative of cosine is sine composed of g of x, which is 5x, so we'll plug that in for g of x, and then plus our constant of integration. So this will yield sine of 5x plus c. So now we are taking the indefinite integral of x times x squared plus 1 to the power of 2 with respect to x. So here we are letting g of x be equal to x squared plus 1, and our first derivative, g prime of x, is equal to 2x. So now we can rewrite the indefinite integral as g of x to the power of 2 times 1/2 g prime of x dx. So we multiply by 1/2 because we want to match this expression here, the x dx. So since there is not a 2 in front of the x right here, we need to divide our derivative by 2 to cancel out the 2 right there. So now we can integrate our g of x to the power of 2. So that'll be g of x to the power of 3 divided by 3. And then we also had our scalar right here, the 1/2. So we need to bring that down again. And then we add our constant of integration because this is indefinite. So now our final antiderivative is equal to x squared plus 1 to the power of 3 divided by 6 plus our constant of integration. Now we have another example. So we are told to calculate the indefinite integral of the square root of 2x minus 1 with respect to x. So now we are letting u be equal to 2x minus 1, and the derivative of u with respect to x will be equal to 2. So we'll have du is equal to 2 times dx. Now once again, we must multiply our derivative by 1/2 because we want there to be just a dx. We don't have a 2 dx, we just have dx. So in order to get rid of this 2, we divide by 2. So now our indefinite integral will be the square root of u, because we have the square root, and we said u was 2x minus 1. So we have square root of u times 1/2, and we are integrating with respect to u. So we can take out our scalar. So now we will have 1/2, and we will integrate u to the power of 1/2. So that will yield u to the 3/2 divided by 3/2. And then we need to add our constant of integration. So this term turns into 2 times u to the 3/2 divided by 3. So the 2's will cancel out, and we are left with 1 divided by 3, and then times u to the 3/2 plus c. And we said u was equal to 2x minus 1. So we can just back substitute the 2x minus 1. It will be 1/3 times 2x minus 1 to the power of 3/2 plus c. We have the indefinite integral of x times the square root of 2x minus 1 with respect to x. So now we let u be equal to 2x minus 1. Then our derivative will be, our derivative of u will be du is equal to 2 dx. So now plugging back in our u. So for this expression right here, we will just have the square root of u. And then once again, we need to multiply by 1/2, multiply by 1/2 to our derivative, so that we will be left with our initial expression, just dx. We just want the dx. We want to get rid of the 2. And then for the x expression, we plug in u plus 1 divided by 2. So that when we plug in 2x minus 1 for our u, we will have 2x divided by 2, which is x. So it will match our x, and then it will match our square root of our u, and then our final dx. So now that we have everything matching our initial expression, but now in terms of u, we can distribute the u's, and we will have u to the 3/2 plus u to the 1/2, and we are integrating with respect to u. And then we can take out the scalar 1/4. We got it from this 1/2 times the 2 right here. Sorry, the 1/2 times the 1/2 over here. So that'll be 1/4 of this integral right here. So now the integral of u to the 3/2 will be u to the 5/2 divided by 5/2. And the integral of u to the 1/2 will be u to the 3/2 divided by 3/2. And then we need to add our constant of integration because this is an indefinite integral. And once again, bring down the scalar, the 1/4. So now after simplifying and back substituting our u is equal to 2x minus 1, our final antiderivative will be 1/10 times 2x minus 1 to the 5/2 plus 1/6 times 2x minus 1 to the 3/2 plus our constant of integration, c. So now we have a trig function, and we are integrating using substitution. So we will calculate the indefinite integral of sine squared of 3x times cosine of 3x with respect to x. So in this case, we will let our u be equal to sine of 3x. So that means when we take the derivative, du is equal to 3 times cosine of 3x dx. Now we will need to divide our du by 3, so that it will match our cosine 3x dx. There is no 3 in front of the cosine or in front of the sine. We're not multiplying by a 3, so we need to get rid of it to match our initial expression, so we divide by 3. So that is equivalent to doing 1/3 of du. And then we can just put our u squared, because we said sine of 3x was our u. So we need to put back the exponents. We have u squared times 1/3 of du, and we are integrating. So we can take out our scalar, and the integral of u squared with respect to u is u to the 3 divided by 3. And then we are adding our constant of integration because, once again, this is an indefinite integral. So then multiplying, we have 1/9, and then back substituting our u, which was sine of 3x, so we have sine cubed of 3x plus c as our final antiderivative. So if the function u is equal to g of x has a continuous derivative on the closed interval from a to b, and the function f is continuous on the range of g, then the integral from a to b of f composed of g of x times g prime of x with respect to x will be equal to, so now our integration limits will be evaluated. We're evaluating our g of x at each of the limits, so they will be g of a to g of b, and we are integrating f of u with respect to u. So the proof is done using the fundamental theorem of calculus. Now here's an example where we change the variables and the integration limits. So we are told to calculate now we have a definite integral. So we're calculating the integral from 0 to 1 of x times x squared plus 1 to the power of 3 with respect to x. So we let our u be equal to this expression here, x squared plus 1. So then that means that our derivative of u, du, will be equal to 2x times dx. So once again, we need to match the x dx. So we will divide by 2. So that's why we have our 1/2 du. And then we have our u to the 3, our u cubed. And then now our limits are 1 to 2, because we said g of x was equal to x squared plus 1. So g of 1 will be 1 squared plus 1, so that is 2. And g of 0 is 0 squared plus 1, and that is equal to 1. So that is why our new limits are from 1 to 2. And then we have this expression which we just went over. And now we will have 1 over 8 times u to the power 4. And we will now be evaluating from 1 to 2. And then we can plug that into our original function, so we will back substitute once we are evaluating our antiderivative. So that yields 1/8 of 16 minus 1, and that is equal to 15 divided by 8. Now we are integrating x divided by the square root of 2x minus 1 with respect to x, and we are evaluating at the limits 1 and 5. So we will let u be equal to the square root of 2x minus 1. So then, isolating the 2x, we can take the square, we can square both sides. So now we will have u squared is equal to 2x minus 1, and then we can move over the 1. So now we'll have u squared plus 1 is equal to 2x. So then 2 times u du will be equal to 2 dx, or 2 du is equal to dx. So now we can evaluate our g of x at 1 and at 5. So g of 1 will be equal to 2 times the square root of 2 times 1 minus 1, so that is equal to 1. And g of 5 is equal to the square root of 2 times 5 minus 1, that is the square root of 9, which is equal to 3. So those are our new integration limits. And now we can plug in all of our u's and du's. So upon doing so, we can take out our scalar, the 1/2, and multiply by the integral from 1 to 3 of u squared plus 1 with respect to u. So now we can integrate. So the integral of u squared is u cubed divided by 3, and the integral of 1 with respect to u is u. And now we can evaluate from 1 to 3, or from 3 to 1, sorry, and then multiply back our scalar 1/2, and that should yield 16 divided by 3. So now we have integration of even and odd functions. So our theorem states, let a function f be integrable on the closed interval from negative a to a. If f is an even function, then the integral from negative a to positive a of our function f of x with respect to x will be 2 times the integral from 0 to a of f of x with respect to x. Now if f is an odd function, then the integral from negative a to positive a of our function with respect to x will be equal to 0. So now we are told to compute the integral from negative pi over 2 to pi over 2 of the function sine cubed x times cosine of x plus sine of x times cosine of x with respect to x. So first we want to determine if our function is even or odd, so that we can apply one of the previous rules that we just went over for even or odd functions, because our limits are the same with opposite signs, same number with opposite signs. So in order to determine if our function is even or odd, we can plug in a negative x every time we have an x in our function. So we will have sine cubed of negative x times cosine of negative x plus sine of negative x times cosine of negative x. And we get that that is equivalent to f of negative x. So that means that our function is odd, and therefore the integral from negative pi over 2 to pi over 2 of our function with respect to x will be equal to 0.